Good morning, everyone. How are y'all doing? Doing pretty good. Doing pretty good. Kind of got a lot to go through today, though. Oof. All right. All righty. Okay, let's. Yes, correct. The quizzes are always going to be over the same material as the homework, the same sections. So yeah, it's just wait to 16. Yeah, 16.2. Yeah, not 16.3. It doesn't do the conservative vector fields. Yeah. Okie doke. All right. So today we're going to look at surface integrals of scalar functions. I believe this is 16.4, if I'm not mistaken. No. Yes, I think. Should be. Yes. Let me just say scalar surface integrals. Our surface area and scalar surface integrals. So we covered a lot yesterday, and I don't really have time to go back and sort of review over that. So we're just gonna power ahead here. Okay. So we saw last time that if we can parameterize a surface by, so with the parameterization using two variables, usually we call them u and v, but in practice, we almost never actually call them u and v because it's more convenient to use other coordinate systems or use x and y. But so we say x, we write in terms of u and v, y we write in terms of u and v, and z we write in terms of u and v. And u and v live in the uv plane and some region d in the uv plane. Usually we use another coordinate system or a specific trick for graphs of functions to parameterize. And we'll see those again later today when we do some examples. So we saw a normal vector to the surface at the point given by g of u naught v naught. So if we pick specific values for u and v, and we look at the point on the surface corresponding to that, the normal vector to the surface, or the normal vector to the tangent plane to the surface at that point, is the partial of g with respect to u at u naught v naught cross the partial of g with respect to v at u naught v naught. So g is a vector function of u and v, and we go component by component. So for g sub u, we take the partial of each component with respect to u, and then plug in u naught v naught. And for g sub v, we take the partial of each component with respect to v, and then we take the cross product, and that's going to give us a normal vector to the surface at the point corresponding to g of u naught v naught. Okay, so we can use this to derive an integral for surface area. And in the interest of time, I'm not going to derive it. I usually like to, but I feel like that's going to put me behind. And if you really want to see it, then you can see where it comes from in the book. But I'll just give you the integral here. So if S is parameterized by g of uv, and u and v live in D, then the surface area of S is so it's going to be the double integral over the region D. So remember, this is just a standard double integral because we're integrating over a region in the UV plane, which is just the plane. It's just a regular old double integral. So we're going to be integrating with respect to area here. We'll bring in integration with respect to surface area later, but for now, this is just a normal double integral in the plane. So we're integrating the magnitude of GU cross GV, that normal vector, with respect to area. So the book says du dv here, which I guess is fine because it doesn't. We don't usually call them u and v, but the order obviously depends on what the region D is shaped like. So it might make sense to integrate with respect to v first, but once again, we don't call them u and v usually. So whatever, it's a normal double integral over a region in the plane. So we parameterize our surface with G, and then u and v live in D. To get the surface area, we integrate the magnitude of the cross product, GU cross GV. So we get that normal vector, and then we integrate that over the region D, where u and v live. So there's another way to write this, and this will bring us into surface integrals. So remember, if you want to find the area of a region in the plane, you just integrate 1 over that region with respect to area, dA. If we want to find the length of a curve, right, we just integrate 1 over that curve, so it's a line integral, with respect to arc length, et cetera, et cetera. If you want to find the volume, you integrate 1 over the region with respect to volume, et cetera. So if you want to find the surface area of some surface, we integrate over the surface S, 1 with respect to surface area, d capital S. So don't get this mixed up with lowercase s. Lowercase s is arc length. Capital S is surface area. Kind of unfortunate, but that's how it goes. So it's a double integral because we're integrating over a 2-dimensional region, a surface. So you want to find the surface area, you integrate 1 over that surface with respect to surface area. So d capital S means with respect to surface area. Okay, so if similar to line integrals, if we look at these two things, then this tells us how we're going to do integrate functions, general functions over surfaces rather than just the function 1. So what we do is we parameterize S if it's not already parameterized with G. So G of UV, U and V and D. So we parameterize. So this is exactly like we do line integrals, essentially. You parameterize, you go to your function, you replace X, Y, and Z with the parameterizations in terms of U and V. We integrate over D now, where U and V live. And then now, instead of having dr or d little s, like we did with line integrals, we have d capital S. And d capital S becomes this magnitude gu cross gv dA. So let me write that down. So S is parameterized by G of UV, where U and V live in the region D in the UV plane. Then, and some other assumptions that are always true in this class, so don't worry about it. If we want to integrate f of x, y, z over our surface S with respect to surface area, d capital S. I'm really emphasizing the capital S there. So if we want to integrate a scalar function over a surface, what we do is we replace x, y, and z with their parameterizations. So x we write in terms of u and v, y and z in terms of u and v, replace those in the function. We now integrate over d, where u and v live. And ds becomes magnitude gu cross gv dA. So if you need to, which we usually will, we need to parameterize S. So we parameterize our surface if we want to evaluate these surface integrals. And then we replace X, Y, and Z with parameterizations. Oops. So this is the exact same process for line integrals, except that ds we replace with magnitude gu cross gv dA. And then we integrate over d. At that point, it's just a standard double integral. So that's the whole point of these parameterizations is we're integrating over these curved regions in space, but we can bring them back to nice flat region in the plane where we know how to integrate over. And it's just a standard double integral at that point. But also you need to remember that the surface area is just the integral of 1 over the surface with respect to surface area. Okay, so this is three simple steps to write down, but in practice, step 1 and step 2, well, all of these often take are rather involved. And so let's go step by step, make sure we don't get lost, and do some examples. Okay. So let's find the surface area. Of the surface S, the piece of the cone x squared plus y squared equals z squared above the disk x squared plus y squared less than or equal to 4 in the xy plane. So that's our first task. Find the surface area of this guy. Number 2, then we want to so that's our A. Then we want to evaluate the integral over S of x squared z with respect to surface area. Okay. So, as will basically always be the case with surface integrals, the most crucial step is correctly parameterizing your surface. Because if you don't correctly parameterize your surface, everything that follows after is going to be off. Okay. So we saw we have a few options, really kind of two options for parameterizing surfaces. We can either use a convenient coordinate system, so cylindrical or spherical, and use the equation of the surface in that coordinate system to replace one of the variables so that we only have two parameters. Or we can parameterize it as the graph of a function. In fact, either of those will work here, but there's definitely an easier thing we can do here. So quick sketch of the region we're dealing with. So it's the cone, z squared equals x squared plus y squared, which is a double cone, but we only want the top half. We want the piece above x squared plus y squared greater than or equal to 4. Sorry, less than or equal to 4 in the xy plane. This is our surface S. Okay, so we want the region above that. Okay, so you could, since z is positive, you could just say, since we're only getting the upper half of the cone, you could just say, take the square root of both sides of the equation and just say z is equal to positive square root x squared plus y squared. That's totally fine. Things are going to get a bit not nice if you do that, though. What we can do, though, is we can use cylindrical coordinates. To parameterize this. Okay. This is nice because, well, we'll see why it's nice in a sec. But okay, so cylindrical coordinates. Let's write the equation of our surface in cylindrical. So instead of x, y, and z, we're using r, theta, and z. So we get z squared equals, and what is x squared plus y squared? R squared, careful, yeah. So z squared is equal to r squared. So z would be equal to plus or minus r, but we're only looking at the top half where z is positive. So we just get the equation of this guy is just z is equal to r. Or we could, as we'll, in fact, it doesn't really matter, but as we'll see, we could just say r is equal to z. We can replace either one. It really does not matter in this case. You know what? No. Let's stick with z equals r. That's fine. Literally means the same thing. Okay. So normally in cylindrical, we have three variables, r, theta, and z, but this says that z is equal to r. So whenever we see z, we can just replace it with r. So our parameterization is, so x is r cos theta in cylindrical. Y is r sine theta. And z is z, but we're using the fact that on our surface in question, z is equal to r. Oops. So z is r. So now we only involve two variables, r and theta. So I'm just going to write it out like this because we're going to take a cross product and stuff. So x is equal to r cos theta. Y is equal to r sine theta. And z is equal to r. That's half the parameterization. Now we need to figure out what the bounds for r and theta are. Okay. So what are the bounds for r and theta? So remember, for cylindrical, if you want to find the bounds for r and theta, it's easiest to project your surface down to the xy plane and then just use polar. So when we project our surface down to the xy plane, conveniently, we're told this is the piece of the cone that lies above the disk x squared plus y squared less than or equal to 4. And so that disk is our projection down to the xy plane. And so r goes from what to what? Zero to 2, right? And theta, of course, goes all the way around. So from 0 to 2 pi. So that's our region D, where our parameters r and theta live. So that's our step one. We parameterize our surface. Okay. So with parameterization in hand, now we need to calculate g sub r cross g sub theta. And so I just want to say, don't get this mixed up. Whenever we write the formulas for everything, we use u and v, but we almost never actually use u and v. We call our parameters other stuff, usually variables from other coordinate systems or x and y. Okay, so step 2, we want to know the surface area. So that's the integral over our surface S of 1 with respect to surface area. Sort of put that in parentheses because that's the thing we're trying to do. Okay, so we go to our function 1. We replace x. Well, let's do gr cross g theta first. So d capital S is magnitude gr cross g theta dA. Okay, so let me, here our g again was, so r cos theta, r sine theta, r. So our g sub r, we go component by component and differentiate with respect to r. R cos theta becomes cos theta. our sine theta becomes sine theta, and r becomes 1. And then our g sub theta, our cos theta becomes negative r sine theta. Our sine theta becomes our cos theta, and r becomes 0. So our gr cross g theta, going to do that really quickly. So we got cos theta sine theta 1 cross negative r sine theta, r cos theta 0. Do your little plus minus plus bit. I'm just going to calculate this really quickly. So we get negative r cos theta negative r sine theta. And then r cos squared plus r sine squared, which is just r. So then, the magnitude of that I'm not going to write it down again. So the magnitude of negative r cos theta, negative r sine theta r is, so we have, let me just write it down, square root of r squared cos squared theta plus r squared sine squared theta plus r squared. So r squared cos squared plus r squared sine squared is r squared plus r squared is, so square root quantity 2r squared, or square root 2r. We can pull the squared r squared out as just r. Okay, so now we have the magnitude gr cross g theta. Now we just need to put the integral together and then calculate. Okay, so I'm going to do that now. If you need me to go back, I'll do that in a second, but let me do this integral. So we want the surface area, so that's the integral of 1 over the surface S with respect to surface area. So what we do is we integrate over the region D. I'll do this like one step at a time. We go to our function, 1, replace x, y, and z with the parameterizations. Well, it's just a constant, so it's still 1. And then ds becomes magnitude gr cross g theta, which we said was square root 2 times r dA. So that's our magnitude gr cross g theta dA. Whoops. And so d, just a reminder, this is our d. R goes from 0 to 2. Theta goes from 0 to 2 pi. Be careful. Do not get mixed up here. So we are in the r theta plane. This is a very common mistake, right? R goes from 0 to 2. Theta goes from 0 to 2 pi. this is not a polar region. We're not going to switch to polar here. We've in essence sort of already switched coordinate systems. So dA, we're not going to change to rdr d theta. dA is just going to be dr d theta. Is there any confusion on that point? We've essentially already done the coordinate switch here. So we're not using polar coordinates here. We're not integrating over a polar region. We're integrating over a rectangle, right? R goes from 0 to 2, theta goes from 0 to 2 pi. So our dA here is just dr d theta. So let me just say, when you parameterize your surface, how do I want to phrase this? Just ignore what we call the variables. It may look like we're like changing to like polar and need to change dA to rdr d theta. Ignore that. Just look at what the bounds for those variables are. And then dA just becomes dr d theta. Because we're in the r theta plane, not in the xy plane, not in some polar region in the xy plane. And hopefully that'll become clear when we do more examples. But it's a very common mistake to make. OK. So this is a very straightforward integral. When we do this, we get 4√2 pi for the surface area. And then for part B, it asks us to evaluate another surface integral, but we've already done almost all the work here. Now we just need to plug everything in and evaluate. So we needed to evaluate the integral of x squared z over the surface S with respect to surface area. Yes, I will, Nate. I will, sorry. So we do the same thing, exactly the same thing. We're integrating the same thing, except now instead of integrating 1, we're integrating x squared z. So we need to replace x, y, and z in our function with the parameterizations. So remember, x is r cos theta, y is r sine theta, and z is r. So x squared z becomes r squared cos squared theta, z becomes r, and then ds becomes square root 2r dr d theta. Oops. So that's our z. That's our magnitude g cross g theta. Oh my goodness, why are you like this? There we go. And so putting it all together, we get square root 2 r to the 4 cos squared theta. That's another relatively straightforward integral if you remember the cos squared substitution. And we should get 32 root 2 pi over 5 for our answer. OK, I will go back a slide real quick and let me know when you're done. Okay. Alrighty. I want to do one more example. Gonna power through this because we really need to do as many examples as possible. So we're comfy with this process. But let's do that. And I'm going to give you a shortcut on this example that you should have memorized for the future because it comes up pretty often. Oops. So let's calculate the mass of the sphere of radius 5 centimeters. 5. If it has density in spherical. So if we write the density in spherical coordinates as 3 cos squared phi grams per centimeter squared. So that's the density of our sphere of radius 5. Let's calculate the mass of this guy. So same thing, you want to find the mass or the total of something given a density over a surface. You integrate the density over that surface with respect to surface area. Yeah, that's fine. Mass is going to be the integral of the density in this case. Okay, so, all right. So step 1, we need to parameterize our sphere. We've done this before, but it sort of gives us a hint here by giving us the density in terms of phi and theta. So that should tell us that our parameters are going to be phi and theta to begin with when we parameterize. Okay. So let's just center our sphere at the origin. It's a sphere of radius 5. So normally x would be rho sine phi cos theta, y would be rho sine phi sine theta, and z would be rho cos phi. But that's rho phi and theta. We need to get rid of one of the variables. And so we need to write the equation of the sphere in spherical. So in spherical, the sphere centered at the origin of radius 5 means rho equals 5. Right, that's the set of all points distance 5 from the origin. And so we're going to use that and replace rho with 5 for our parameterization. So x is going to be 5 sine phi cos theta. Y is going to be 5 sine phi sine theta. Z is going to be 5 cos phi. Right, so we've replaced rho in all of these with 5. And so now we're just left with the parameterization in terms of phi and theta. Oops. Dude. So g of phi theta is going to be x is 5 sine phi cos theta, y is 5 sine phi sine theta, and z is 5 cos phi. And we need to get our bounds for phi and theta. There's my beautiful sphere. So we're getting the entire sphere. So phi goes from 0 to pi, right? We have stuff on the positive z-axis, stuff on the negative z-axis. Phi goes from 0 to pi. And we go all the way around the z-axis. So theta goes from 0 to 2 pi. So we have our parameterization of our sphere. Spheres come up a lot. It's good to remember how to parameterize these. Okay, so the cross product is a little hairy. There's a lot of simplification that goes on. And so let me just give you something which you should remember. So for a sphere centered at the origin of radius r, let me say radius capital R, so we'll just look at magnitude for now. We'll look at the other one later, but so the g phi cross g theta hang on. We'll just this later if we need to. That's just going to be the radius squared sine phi. And this is, in fact, easy to remember because we've already seen something similar to this. We've seen a rho squared sine phi when we convert dv becomes rho squared sine phi d rho d phi d theta. Here we get something similar, except it's r squared sine phi. And that's, you're just replacing rho with the radius of the sphere. So just think the radius of the sphere squared sine phi. So the rho squared sine phi. That's what your magnitude of the cross product is going to be. That's saving you a big hassle by remembering that. So you should memorize this. Okay, so that's our step 2. Step 3, let's put it all together and integrate. So this is maybe slightly confusing because it gives us the density in spherical coordinates. So that we already have phi and theta there. There's no x, y, and z to replace. So that's the thing we're integrating. So 3 cos squared phi is our mass after we've replaced x, y, and z with the parameterizations. And so phi goes from 0 to pi, theta from 0 to 2 pi. And then let me write it like this. Not mass, that's the density. So mass is going to be the integral over the surface S of the density with respect to surface area. So the density is the 3 cosquared phi. ds, we said is going to be the magnitude of g phi cross g theta, which is going to be the radius squared sine phi. In this case, our radius of the sphere we're told is 5. So that becomes 5 squared, 25. Sine phi d phi d theta. So that's integral 0 to 2 pi, integral 0 to pi, 3 times 25 is 75, cosquared sine theta. So cosquared theta sine theta, d phi d theta. And that's just a simple u sub. When we do that, we end up getting the mass is 100 pi grams. Let me get rid of the grams. It's just the mass is 100 pi.
Is that 25 or 75? That's 25.
That's 75.
75.
Yeah. But we use spheres a lot, integrate over spheres a lot. So this is a very nice time save to remember. This bit up here. Oops. The magnitude of the cross product of that after you parameterize is going to be the radius squared sine phi. I'm going to save you a lot of time. Because not only do you have to take the derivatives, do the cross product, there's a lot of simplification involved, and then you're still taking the magnitude after that. Save yourself the trouble. Just remember that. Okay, so I think tomorrow we'll start off doing one more example of this. We'll do one for graphs, and then we'll move on to the next chapter, surface integrals of vector fields. But yes, any questions? All right, if not, have a great rest of your day, and I will see y'all tomorrow. And make sure to do your quiz and get that uploaded today. And yeah, have a good one, guys.